So I am going to talk about water, but I'm going to talk about water in a special context, and that is in the context of something that's really important around here and really important where I come from, and that is weather. And so I want to talk about water and weather, and I hope to demonstrate to you that something is really important about weather that we haven't realized before, and that is electrical charge, which fits nicely into the theme of this conference. And I guess a shorter title would be, should I bring an umbrella to work? Okay, so let me start with a few questions. So here's a question. Sometimes above the water, you see a single cloud. But that's weird because, you know, the water is evaporating from everywhere, so how come only one cloud when the vapor rises all over? Is there some attraction of moisture that comes and pulls the moisture into this cloud, or something else? How do we understand this? How come there's not one broad cloud that exists over the water? Another one, maybe you haven't thought about this, but what keeps the cloud afloat? Cloud consists of water. Water is heavy. A cloud like this consists of, I could give you in kilograms the weight and such, but it's convenient to talk about the weight in terms of elephants. So this is the equivalent of perhaps 1,000 or so elephants. And how come the elephants don't fall on your head? Maybe that's a question that you haven't thought about, but some people have. And then, you know, in Seattle where I live, we get a lot of rain, and we see dark clouds. Sometimes they release the rain, and other times they don't. And so what gives? How come? What makes it rain, and why sometimes does it not rain? So we're talking about water, and water is something about which we know. So I want to start from a few principles that have been developed over the past years, and then go on from there to talk about how these principles can be applied to get a better understanding of weather. And it starts with this book that Don Scott mentioned, and we uncovered a different phase of water beyond solid, liquid, and vapor. And it comes from a lot of experiments that we did, and I think rather straightforward interpretations. And I just want to give you a summary without presenting the evidence for what we found. So we found that if there's water, and the water sits next to a hydrophilic material, in particular, not hydrophobic, but hydrophilic, water-loving, what happens is that the water transitions into a completely different structure, a layered structure, honeycomb kind of structure that builds in layers from here, one after another, and just keeps going on. And in fact, typically we find up to millions of molecular layers that undergo these transformations. We call them EZ, or exclusion zone layers of water, because we find experimentally that as these grow, they push out all particles and solutes. So it's rather pure substance that we get here that's solute-free. And the structure looks something like this. It's a hexagonal or honeycomb kind of structure consisting, of course, of oxygen and hydrogen. And unlike the structure of liquid water, which sits out here. And it turns out it's not H2O anymore, it's actually H3O2. If you count the oxygens and hydrogens in a unit cell, this is what you get. And it's not surprising because experimentally we found that this region has a net negative charge. And this is negatively charged. If to be neutral, it would have to be H4O2, that is double H2O, that's neutral. But it's negatively charged. If you wanted this to be neutral, you'd have to put one more proton in here to make it H4O2. So negatively charged, and the positive charges complementary positive charges lie here in the water. And the reason is that in order to build these, what happens is the water molecule is breaking into its component parts into OH minus, which sits here, lines up to give you this structure, and H plus, protons. So this is negative, and this is positive. And what that does is to form a kind of battery. This is the hydrophilic surface. This is the water. And this negatively charged EZ, or we call it fourth phase of water, is sitting here. And the complementary protons are sitting here. It's got potential energy, just like a battery. And in fact, the energy to charge this comes from light. We found that. So the question is, how does this potential energy play into weather? Everybody's interested in the weather. Nobody really understands it. And I think the answer is profoundly. And I want to present to you some, well, rather than really evidence, some of it is evidence and some of it is conjecture, to give you perhaps some idea that differs from the conventional idea and what is responsible for weather. We start with the water cycle, and many of you have seen this before. Here's the atmosphere and the clouds, and we have precipitation, which could be water or it could be ice and snow, and the groundwater flows down into the oceans, and it evaporates, and the evaporated water condenses, and so on. And so some of the water that exists, it can be millions of years old, same molecules that get recycled over and over. And so we deal with ice and snow, we deal with snow melt, evaporation, condensation, and then precipitation. And that's what I want to talk about. And I'd like to present to you and argue that these are qualitatively different from what you think what you might have learned. So we're going to talk about this water cycle and weather, and I want to talk first about water and ice, which you saw on the upper left, then evaporation, condensation, precipitation, and then wind, something that many of us never really think about, but it's certainly around, and weather exotica. I'm not sure how much I'll get through, but let's see. So we start with water and ice. So you know about ice. You just basically take water and freeze it, and you get ice. But it's not quite so clear as that. It turns out that this fourth phase that I mentioned to you is a necessary condition for the freezing of water. So we all think that when you freeze water, you go from water to ice, but what we found, and is described in the book, and I'll show you a few slides, is that water doesn't really transition directly to ice. It transitions to EZ, whose structure is not so different from ice. It's not ice, but not so different, and then to ice. And if you melt the ice, you go from ice to EZ and then to water. So the process of freezing differs. And the way it works is something like this. You start with the EZ structure. Remember, there are these hexagonal sheets that pile on one another. You may not have noticed it, but each sheet is slightly displaced from the sheet behind it. It's displaced in such a way that the negative oxygen here lines up with the positive hydrogen here, and so these are electrostatically attracted, and the same here. So it's a stable structure. It sticks together. And what we found is that the ice forms as this EZ structure. Remember, you go from water to EZ and then to ice. What happens is that you add protons, and I'll explain how in a moment, and these protons, positively charged, insinuate themselves between the two negative oxygens here, and then there's a shift of planes so that the planes are no longer displaced from one another, but they're actually in register. And that's when the planes come apart so that the ice is less dense and the ice floats. And, you know, we're happy that ice floats, because if it didn't float, if the ice were more dense and that the ice began from the bottom and worked its way up, then you'd have a real problem, because creatures like this could be maybe in cold climes, could be basically pushed out of the water and would obviously perish. So we're lucky that the structure of ice is less dense than the structure of water. So let me show you the evidence. Is it really necessary? Is the EZ really necessary for ice formation? So here's a simple experiment. What we do is we take a droplet of water and we put it next to a hydrophilic material. This is one that we commonly use. It's called Naphion. And so what we find is that next to the Naphion, we have EZ water that forms. And beneath this, we have a cooling plate. So basically, this water is being cooled, and eventually it turns to ice. But I want to demonstrate to you that it's the EZ that where the ice formation is initiated. And that's shown here. So we're depicting this particular region over time. And so here's a water drop, and here's a piece of Naphion. And remember, the EZ is sitting right here. And you see this bright spot. This bright spot shows the initial location of ice formation. And later, as ice formation occurs, of course, it moves into the water, but it moves and penetrates down where the EZ is. And you can see later, it basically follows the EZ. So the EZ is basically the first place to freeze. The freeze initiates in the EZ, and that's the main point. And the way we think it does, and I'll show you evidence in a moment, is that you have the EZ here, remember, negatively charged here, and the protons here. And gradually, as the EZ builds up, more negative charge, you get more positive charge here. And when the positive charge gets dense enough, what happens is it moves into the lattice all the way to the most negative part and forms here. And remember, EZ plus protons gives you ice. And so we have the ice that forms right here. And the process continues, and gradually you get a whole bunch of ice, starting with the EZ. Now, to show you that this really happens, we have a setup that looks like this. So here's a chamber. This is a thermoelectric cooler. So this water then gets progressively cooler. And we find that the cooler it gets, the bigger the EZ gets. And beyond that, we just have water, and we put pH-sensitive dye. These are the dyes, that change color, just like litmus paper. Acid is one color, base is another color. And here's what happens when freeze occurs. So here's the cooling plate, right? Here's this cooling plate. Here's the ice, and here's the water that has yet to convert to ice. So the green color is actually neutral. And here in the ice, the red color is very low pH. It means it's full of protons. So it shows that, indeed, as the ice forms, a lot of protons enter into that region. So ice formation involves protons. It's EZ, negatively charged, plus protons give you ice. So we understand now that what happens is you reduce the temperature, you get EZ builds up, and all the protons that are sitting here rush into the EZ, whose structure is a little bit different from ice, and that converts to ice. So what happens when the ice melts? Well, you might expect the opposite, or the reverse process. So the ice turns into EZ, which then turns into to water. So do we really see EZ water when this melts? We did the experiment. We put ice into a cuvette and allowed it to melt, and put the cuvette into a spectrometer, which can measure the absorption of light at different wavelengths. And so we asked the question, does melting produce EZ water and protons? So this is the absorption spectra of just melted ice, just melted water samples. And there are 4 different panels, and the only difference between them is we used a different kind of water. So this is deionized water. We use that to make the ice. boil deionized water, degas deionized water. It doesn't really matter what kind of water you put in there. When you melt the ice, you get a similar spectral pattern. In all cases, there's a big absorption peak at 270 nanometers. And we know from our previous experience that the 270 nanometer absorption is the signature of easy water. It's the defining feature. That water absorbs light in the UV region at 270 nanometers. Ordinary water doesn't. So we can conclude that as you take the ice and you melt the melted ice is easy water. So the melting is ice to easy, and then finally, after some time, the easy converts to ordinary water. So what about snow? Well, it's pretty. And I think all of you know that snow has hexagonal crystals, and it's always been a kind of mystery as to why they should be hexagonal. But remember, the EZ is hexagonal, and if snow grows from hexagonal kind of ordered water, it makes total sense that the snowflake would actually be easy, some construct of easy water. And the fact that easy water is negative means every snowflake should have negative charge, and these snowflakes should stay apart from one another, which basically they do, built from, from hexagonal EZ. So we've dealt with ice and snow and the fourth phase of water, and I've presented to you some features that are perhaps a lot different from what the conventional view is of freezing and melting. And now I'd like to show you a video. And this video is something that is on the Discovery Channel, and it was based on my book, The Fourth Phase of Water, and we made it, you might say, to Hollywood, and I want to show you a 5-minute clip. The movie is called The Fourth Phase. It was done by a famous snowboarder, Travis Rice.
From when I was a kid, I've always been intrigued with water and how we interact with it. Since then, traveling the world snowboarding, the concept for this trip evolved to follow the hydrological cycle around the North Pacific.
Really attempting to immerse oneself in the elements and see how this whole thing works. It's been incredible.
As children, we're all motivated to find the truth. A child looks around and is learning truths all the time. We have this natural tendency to explore. I'm Gerald Pollack, and I'm a professor of bioengineering at the University of Washington in Seattle. It can be really challenging to keep an open mind in these days. Scientists have become more hesitant to challenge perceived truth. How are you doing, Lee? So it's working? Yeah. There are some books that suggest that essentially we've kind of reached the limit of what there is to know. I'm shocked by this perception. There are many aspects of water that we see every day, and we don't really understand them. These are questions that need answers. We all learned that water has 3 phases: the solid state, the liquid state, and also the vapor state. However, you can't explain all the known properties of water with 3 phases alone. You need a 4th phase. What's the 4th phase? With an energetic input, water molecules undergo massive change. They become ordered, they acquire charge. All of this energy to create the order comes from light. We began with experiments to try to learn more. We noticed something that seemed almost magical. Every one of the tests that we did showed that this water was different from ordinary water. The individual molecules actually link together to form a hexagon, and then many hexagons. We can understand why snowflakes are hexagonal. They actually form from the fourth phase of water. After some time, there seemed to be enough evidence to indicate that this was a distinctly different phase of water. You might ask what implications it has for us. We're approximately 2/3 water. Most of the water inside of our cells, they're filled with fourth phase water. This could be central to all of what goes on in the biology of the cell. This is going to lead the way to a better understanding of how cells function.
I think part of the beauty of the fourth phase, especially as it relates, I guess, to this film, is the concept that not everything is as it appears to be. Leaving some space and open-mindedness for allowance of a shift in perspective on how you view the world is one of the most important things in my life.
Being a scientist is a search for truth. We somehow need to change the system so that we're looking for ideas whose outcome has the capacity to really shake the earth and create breakthroughs, if not revolutions. You need to dig deeper and deeper in order to find the truth. Thank you. This was cool, and I'm really shocked that these guys actually survive what they do in the backcountry. Okay, so I talked about water and ice, and I tried to demonstrate that the formation of ice and the melting of ice is different from what we think. And I want to talk about evaporation, and the message is the same. It's not what we think. So what do you think about evaporation? You probably think that you've got a glass of water, and it's evaporating one molecule at a time. A molecule gets a kick of energy, of kinetic energy, and it comes up. At least that's what I learned. And the reality is a lot different. So let me start with this. This is taken at Starbucks. Seattle, Starbucks was born in Seattle, so we drink a lot of coffee. And if you have a dark background, you notice this is a hot latte, I think, and taken by my son. And you notice something interesting. You can see the vapor. Now, if you can see the vapor, what does that mean? Well, you can see the vapor because the light is being scattered, and you don't see a hell of a lot unless the scattering entity is at least on the order of the wavelength of light. Wavelength of light is half a micrometer, where it turns out that these are little tiny droplets in here that are tens of microns. Now, even 1 micrometer little droplet contains, do you know how many water molecules? You can do the arithmetic. It's something like 1 billion on that order. So there's something wrong appears to be wrong with the idea that the evaporative entity is 1 molecule, unless they come together above here. And we know they don't because we've checked we've checked these when water is evaporating, and we can check right just above the surface as this is emerging. It's no different from what you see here. So that idea seems to be incompatible with basic physics. Well, another interesting feature is that it's not continuous. Look, it seems to be discrete. Now that's a surprise because most of us, we presume that the evaporative process is a continuous one. Not only is it discrete, But also it appears to come from one region of the water, not necessarily from the entire surface simultaneously. Well, I have a lot of undergraduate students working in the lab, and many of them don't do what I tell them to do. They have minds of their own. And there was one guy, there's a Chinese student, we have a lot of them in Seattle, and he was curious, and so he took a laser beam, and what he did is to condense the beam into a plane, and he wanted to get a cross-section of one of these would look like. So what do you think they look like? You might think a cross-section would look like kind of cotton or something like that, but it doesn't. It looks like this. These are 4 different experiments, and you can see, looking at, let's say, this one, that the bright area is scattering light. It means that's where the water is. In between that, the dark area is doing nothing, so it seems to be essentially empty. And I got to tell you that when I saw this for the first time, I almost fell out of my seat because I couldn't believe that the evaporative entity had structure just like this. It seemed inconceivable, but after enough repeats of the experiment, it was pretty clear that this was correct. So the first thing, well, sorry, it wasn't the first thing, but we thought, this is not created from nothing, this kind of pretzel-like structure. There must be something in the water that may be giving rise to this kind of pretzel-like structure. So we raised the question, is there a corresponding structure in the water itself? I'm not sure if you can see it, but I can see it on my screen. If you look into the warm water that you see here, and this picture was taken by my son, who's the artist of my book, and I was really pleasantly surprised to see this. This one was at home, I think, not in Starbucks, but I can see it here. I hope you can. There's a mosaic structure. If you can't see it, then take a look at this one. This is an experiment you could do yourself. So this is a pan of warm water, and it's illuminated not from above, but at a glancing angle from the side. You might call it dark field illumination. And you can see the same sort of structure, low angle illumination. And so it looks like the warm water that's evaporating does contain some kind of structure, as the previous slide showed as well. And we can also see it by using an infrared camera to look down at the warm water. And you can see same sort of structure. So there's no doubt that the structure is there. Well, the usual interpretation when you use an infrared camera is that this region looks warmer than this region. In fact, conveniently, they actually provide a scale for you so you can correlate the darkness with the equivalent temperature. But it's not necessary that that's the only explanation. Another possible explanation is that these lines actually denote the presence of easy water. Now, why do I think so? Well, it's because of older experiments that we did. Here's a piece of Naphion next to water. And remember, an EZ forms next to the water. And so the infrared camera is picking up the amount of infrared energy that's being radiated from that. The EZ is dark. It means it doesn't radiate a whole lot. And the water beyond the EZ radiates, as you can see, is brighter. It radiates much more. So dark here, the EZ is dark. And if we go back to the infrared image of this, you have to ask the question, is it possible that the dark region here is actually EZ material? And we think it is because we've looked at the origin of these structures that form. And you can see little dots here, just as they form. And these dots, we don't know whether they're little droplets or little bubbles, but essentially it doesn't matter for us because what we found in our experiments is that if you have a droplet, this is the structure. if you have a bubble, this is the structure. And in both cases, these are lined by layers of EZ material, just like onion skin, and that's what holds it together for both of these. But inside, you have a lot of protons, and the protons are repelling each other. They're pushing out against this skin, and that's what keeps it into a sphere. The difference is that in this case it's liquid, in this case it's a vapor. So we've learned in our experiments about these water droplets, and since we don't really know if they're droplets or bubbles, we call them vesicles. And we do know that the vesicle structure looks like this, and we do know that as they form, before they enclose themselves, these positive charges tend to repel each other, they leak out, and so the amount of negative charge here is always more than the amount of positive charge. So these little vesicles, whether they're bubbles or droplets, have net negative charge. That's important. So if you think about the possible explanation for these dark lines, remember I suggested maybe they contain EZ material. Well, a possible way that they can contain EZ material is shown here, that you have a lot of these vesicles that are stuck together, and so for example, this entire cluster here would represent what we see here, consisting of a whole bunch of these stuck together. How are they stuck together? Well, we presume that they're actually glued by protons, and so these are negatively charged, and this is negatively charged. If you have protons between them, the protons will act as glue, holding them together. Now, this is not a wild speculation. It actually comes from Feynman many years ago, who talked about negative or like charges that come together, and he called it likes like. Well, these negative charges like each other, so they come together. And he said the reason they come together doesn't violate any basic principles of physics. It's because opposite charges gather in between. And so you might have positive charge, which pulls this one and pulls this one. He said likes like, because of an intermediate of unlikes. And I think that's what happens, and that's how you can imagine that these are actually glued together, negative charge here, protons in between, holding it all together. There are many examples of this. I don't have time to present it. So this is an oblique view that shows the same mosaic structure on top. But what this slide shows is that it's not just the surface layer, it actually extends downward. You can see the dark lines coming and extending downward. And what that means is that these mosaic cells are actually mosaic tubes. They extend down into the water. And so when we talk about evaporation, we have a situation that looks like this. This is a kind of conclusion slide, that we have these basically tubes that run down. They're not just on the surface, they run into the water. And when sufficient charge gathers, they actually rise up like this, and then they become vapor. And if you were to take a cross-section of this, it might look something like this. So basically, the vapor patterns that you see, especially in cross-section, come from liquid patterns that are down here. They simply rise up to give you this incredibly beautifully shaped vapor that we see. And you get clusters, so you get one of these groups of tubes that rise. Well, this will be the first one, then the next one, and the next one, and they're actually discrete events. But by the time you get up here, the droplets that make up these clusters eventually dissipate, because you don't see any vapor up here. So they're basically dissipated into the air. And so when you think about humid air, you can think about these negatively charged little droplets surrounded by positive charges, which are known to occupy the atmosphere. However, if there's enough positive charge to glue these together and form clouds like this, then the humidity disappears and it becomes clear instead of humid. And then you can see a difference in your environment. So if you have humid air, you can imagine looking through this humid air to some building that sits at some distance. And the building is not clear, it's fuzzy. And the reason it's fuzzy is that the light that gets scattered from the building, before it gets to your eye, it's scattered by numerous of these rather large little droplets that sit in the air as humidity. On the other hand, if the air is clear, if these little droplets have actually condensed into clouds, then you can see these buildings much more clearly. So those of you who live on the East Coast, you know, Washington, D.C. in summertime, buildings look like this, but in the wintertime, they may look like this. Okay, so that's evaporation and the mechanism. I've presented evidence to you that the mechanism is grossly different from what we think. Okay, now what about condensation? So you've got these droplets in the air. How do they condense into clouds? Why do we get a cloud to begin with? So what we have in the atmosphere, among other things, are two principal constituents. One is these water vesicles that have a negative charge. And we have positive charges known, the atmosphere is known among atmospheric scientists to be net positive charge. And somehow the positive charges are linked, nobody knows exactly how, to molecules in the air. So we have negative charge and we have positive charge. And so we come back to the Feynman's like mechanism. We have these vesicles of water that are suspended in the air, and we have positive charge. If you add these together in the right quantity, you get a cloud, because the positive charge brings these negatively charged vesicles together. So a cloud may look something like this, principally these negatively charged vesicles, and with enough positive charge, these vesicles are actually linked together, and they form these clusters that we call clouds. So, question arises, what keeps clouds suspended in the sky? And I don't know, a lot of people have never thought about this question. Remember, it's water, and water is pretty heavy. Well, we know that clouds have charge. This is one example, probably not unknown to the electric universe people. We also know that the Earth has an electric field, beyond the magnetic field. And the electric field runs perpendicular to the surface of the Earth, and it exists because there are positive charges up here in the ionosphere and beneath, and because the Earth has a net negative charge. And by the way, the net negative charge may come from the EZ water that fills the surface of the Earth and all greenery. So this is at the electric field at the surface of the Earth is roughly 100 volts per meter, which means that my nose is 200 volts relative to my toes. Okay, so good to remember. It's easy. Okay, so we have, what about floating clouds? So the Earth is negative, and the cloud is negative, and so it doesn't take a rocket scientist to figure out that there's a repulsive force between them. But your reaction might be, or might not be, is that repulsive force really strong enough to keep the clouds suspended simply by repulsion? Well, I want to give you two examples that demonstrate it. The first is this. You take an old-fashioned 120-watt bulb, and the current is flowing through the tungsten filament, and suppose you could collect 1 second worth of charge flowing through here, just 1 second, and suppose, thought experiment, you could compress that to a point, and you put that point down here of negative charge, and you do the same thing up here, and they're separated by 1 meter. So the question I ask you is, you know that these are going to repel each other. This one can't go down, but this one can go up. So the question is, how much weight do you need to put on this one in order to prevent it from going up? okay? So I've asked this question. I get all kinds of answers from a gram to a ton or whatever, and the right answer is about 50,000 garbage trucks. Now, knowing that there are Boeing engineers here, the original thought was actually it's something like 5,000 Boeing 747s, but my son, the artist, couldn't draw a Boeing 747 stacked up. So we wound up with garbage trucks, and this is roughly the amount of weight. Now, so we're talking a huge force. Another example is this. So you have a couple, and the guy is lying here, and the woman is suspended somehow. It doesn't really matter how she's suspended. You might think of a net or something that's keeping her away. Of course, they would like to join each other, but she's suspended here. And suppose, this comes also from Feynman, by the way, from his lectures, except he has them vertical, standing instead of in this position. But suppose you're able to remove 1% of the electrons from this guy, and 1% of the electrons from this woman. So she's positive, he's positive. They repel each other. He can't go down, but she can go up. He doesn't want her to go up. He'd rather have her go down. Well, so a question is, how much weight would you have to put on her back in order to prevent her from rising up? Anybody have a guess? How many garbage trucks? Okay. So actually, the number of garbage trucks is so large. The correct answer, remember, according to Feynman, is the weight of the Earth. This is astonishing. So, main point, the force that is generated by charges is much larger even than people in the electric universe, or most of you are I think, thinking. Huge forces. And so we come back to what keeps the clouds suspended, and I think what keeps them suspended is the fact that the clouds have a net negative charge, and the Earth has a net negative charge. So one suggestion is a repulsive force between these and these. That's why the clouds are sitting up there. And if the cloud has more negative charge, then it's going to be higher, and if it has less negative charge, then it's going to be lower. It's a simple paradigm, and that explains what atmospheric scientists have a really hard time explaining, and that is clouds in different layers. So simple explanation is that this cloud has a lot of negative charge, so it's high. This one has a moderate amount, and this one has low negative charge. And so that's how they're suspended. Side issue is this. Think about it. The Earth is negative. The atmosphere is positive. We all know that positive attracts negative, and so you'd expect that simply by virtue of the fact that this is positive and this is negative, they're going to stick together. Now imagine if they didn't stick together. Just think about this scenario for a moment. The Earth is spinning, right? And typical velocity on the surface is, we're talking about something like 2 times the speed of a jet plane. So it means if you went outside and the atmosphere was not stuck to the Earth, there'd be a hurricane outside every time you walked out. So I mean, the atmosphere must somehow stick to the Earth. And this is perhaps a simple explanation that plus and minus cling, and so the atmosphere clings to the Earth. And in fact, if you think about it, a question that might be raised is, does clinging force explain what we know as atmospheric pressure? We think of the pressure arising from molecules pressing on each other, but you know the atmosphere is not a pile of bricks. The molecules are a gas, which means they hardly touch each other, and you can go through various arguments to come up with an idea of how the atmosphere could actually press on the Earth, but a simple argument might be that the pressure comes from the plus sticking to the minus. And that prevents the blow-away scenario, because there are big winds up here, and if you just have stray molecules around and the wind comes, you might expect that we'd have no oxygen left to breathe. Okay, so I talked about the condensation. Now what about precipitation? It does rain, although not so often around here. So what causes the rain? Well, if you listen to the weather people, they'll talk about pressure and they'll talk about temperature. And I don't know about you, but I've never been able to understand how this combination of temperature and pressure could yield rain. So, of course, another question that people here are likely to raise is what about charge? Is somehow charge involved in weather and bringing rain? We know that there's charge there, and I'd like to bring up the principle of induction. This is Faraday induction, which I think is known to many of you. So if you have a positive charge sitting up here, if it's really far away, it doesn't do a whole lot, but if it's closer, it'll begin to induce opposite charge down here, and the closer it is, the larger the opposite charge that's generated. It doesn't matter whether this charge is positive or negative. Basically, the same thing occurs, and this force is always attractive. That is, if you have the negative here, you'll always have positive here, and they attract one another. And I think this principle, this simple principle that we all know about, is really critical. An example of it is here. You take a balloon and you rub it on your shirt, and notice, same shirt as in the movie. It's the only shirt I own. Embarrassing moments. And you put it next to the faucet, and the faucet bends quite appreciably. It's fun, a fun thing to demonstrate for kids. And what's going on? Well, the balloon is charged by the triboelectric effect. Rubbing on your shirt or your hair induces opposite charge, and the two are attracted, and so the stream bends this way. So we have the same principle going. We go back to the cloud, and the cloud, we have the negatively charged vesicles containing the water, and we have positive charges. They come together to form a negatively charged cloud. And when positive charge, more positive charge lowers the cloud, right? It comes closer to here. There's an inductive force, positive here, negative here, and this pulls the water from the cloud. It's a simple pulling force that can do that. So I think a possibility is that precipitation occurs inductively. I'll go back to that in a moment. Now, what about wind? So we know the wind occurs, and we sometimes think that it's the fire of the dragon that creates the wind, but what creates the wind? We don't know. Is it pressure gradients, which I think is what you will read in the textbook? But it's kind of difficult to understand how you get a wind gust. Gust is pretty local, and of course the gust can be powerful, as you see here. And I think it's possible that charge gradients are responsible for wind. And why do I think so? So here's a diagram that you've seen. Here's the Earth, and here's the positive charge in the atmosphere. And it's known from measurements that protons diminish with increasing altitude. So here you have the highest electric field, and it diminishes with increasing altitude. At night, it's very small, possibly because there's not much evaporation, and the positive charges don't get into the atmosphere. During the daytime, it gets much higher, and this is well known. This is not a conjecture. So here is low electric field, and here's high electric field. Now, this is taken from a published paper, and what we're seeing here is the electric field up high in different places on the Earth. So forget this one for the moment. That's integrated over all of them. Let's look at Africa and Europe, and this is GMT. So we see that the peak electric field in Africa and Europe occurs at 1400 roughly GMT. So this is in Africa and Europe roughly early afternoon. It's when the sun is the brightest. The sun is really shining. And you see it's much bigger than in the evening. Look at the Americas. The peak occurs at about 2100. It occurs later than here. Again, it corresponds to when the sun is really up high in the sky. And the difference between nighttime and daytime is huge. It's a factor of 10. There's a big difference between the two. So think about it. The electric field is high here, and it's low here. So that means you've got a gradient, high electric field, low electric field. So in this case, you've got a lot of positive charges here and very few positive charges. The positive charges repel each other. They want to escape. Where are they going to go? Well, they're going to go this way. That gives you wind. And I think with this, I don't have time. I think this can explain both the trade winds that blow from east to west and the prevailing westerlies or jet stream that flows from west to east. They originate at the two different light-dark boundaries. That gives you wind. So what about a gust of wind? Well, I think a gust of wind could occur with a local charge gradient depending on the plants and the structures that exist there. So I think it's possible that the origin of wind comes from atmospheric charge gradients. Now, what about exotic weather? Seattle is not like Phoenix. This is what it looks like in the typical winter time, and we get a fair amount of rain, and people get caught downtown, without their umbrellas, and they rush to their cars. So what's going on? Why, the question is, why in Seattle do we get a lot of rain in the winter, whereas the summertime, it's a bit like Phoenix, although a little bit cooler. And remember, this is the mechanism that we've deduced for clouds. You need the humidity with negative charge, and you need positive charge to bring these together. And of course, you need enough positive charge to bring it together, because if you have a trivial amount, it won't happen. So think about the winter in Seattle. Okay, now, when it's winter in Seattle, in the summer, the Earth is tilted in such a way that in the southern hemisphere, you've got a lot of sunshine occurring, right? And this lot of sunshine builds positive charge way up into the atmosphere. We don't get it here, but we get it here. Now, where does this charge want to go? Well, the charge wants to escape from here, the high atmospheric charge, so it goes this way. Meanwhile, you have the prevailing westerlies going this way, and the two are combined to bring moisture into Seattle in the wintertime. And so you're getting a lot of charge coming in, and the situation is like this. You have a cloud, charge comes, right? And the addition of more positive charge reduces the negativity, so the cloud gets lower. And of course, a lot of these vesicles begin to be attracted to these positive charges. So the cloud because of the positive charge, begins to lower. And because of additional positive charges, these clouds can actually merge with one another. So not only do they get lower, but they get larger. And this keeps happening, gets lower, and it reaches a point where you have an inductive force. The negative charge induces positive charge, and that brings the rain. If it's low enough and it induces enough positive charge, the positive pulls the negatively charged vesicles and we get rain. The rain is actually pulled toward the earth. So rain or no rain, I think the cloud must lower sufficiently past the critical point of inductive inevitability, then it rains. It's sort of like an orgasm, you're almost there and then you're there, if you will. Interesting scientific fact. Some guys, not this one, this one. Some guys used high-speed video to record rainfall. And we all know, if you have a droplet that's falling based on its size and physical properties, you can compute the velocity. Well, they measured the velocity, and they found that it was up to 10 times higher than you could imagine due to the fall. And so they concluded, this was published in Nature, they concluded that there's a pulling force that brings it to the Earth. I need about 3 minutes. Okay. Now, exotic weather. For the Australians who are here, I think this comes from Australia. We have these thunderheads, which can yield intense rainfalls, and notice the curvature around here. If you think about the Earth that's rotating, if you're standing on the equator, it's rotating really fast. If you're standing up here, the speed is pretty slow. And so there's a gradient along here, which means, because this is always faster than this, clouds will always rotate in the counterclockwise in the northern hemisphere that we see here. So if you think about a hurricane, here's a cloud that has negative charge. It's moving in this direction, at least initially, because the trade winds push in this direction. But think about the atmosphere, the positively charged atmosphere. So this cloud is moving in this direction, compressing all of these positive charges, whereas behind it, it's already passed through. There's not much positivity left. It's left a swath where there shouldn't be positive charge. So this negative charge is attracted to a lot of positive charges. The two will tend to combine. And when they combine, what happens is, remember, you get more positive charge with the negative. This part of the cloud descends. It releases its rain, and it becomes clear. And this will be the eye of the hurricane. Meanwhile, the cloud is rotating in this direction for the reason I showed you in the last slide. So you come to here, and again, the same thing happens with this region, and so the eye becomes larger, and it starts curling around until you reach this state where the negative charge, right, induces positive charge, and the eye sticks to this, and it keeps going and building like that, and eventually you get a structure that looks something like this. This is a typical hurricane. And sometimes, you can get one of these not typhoons, but tornadoes. And think about it. Again, we have the rotation occurring here, and what keeps it all together is the first point. And most of these particles here are negatively charged. So you've got positive charge that keeps it all together by the like mechanism. And by the way, you often see lightning discharges in these, so it's kept together. And because it's kept together, this entire thing is rotating. You get fierce winds out here. And because of the charges, the induction force pulls up refrigerators from here. So we get some idea of what is responsible for the tornado. So I've gone quickly through the entire cycle: evaporation, condensation, precipitation, ice and snow, and so on. And I'm suggesting to you that not only are the mechanisms different from what we've all learned, but that a central feature for all of this is charge, negative charge and positive charge. So I would leave you with charge is absolutely critical, and there's not a single weather forecast that I've ever seen that says, hey, the charge in the atmosphere is such and such, and because of the charge, we may expect this kind of weather. So I think one day, if the atmospheric people begin to take into account that the universe is really electrical, we'll know whether to bring an umbrella to work. So I end with the book. The book has become popular, and a lot of the ideas and issues that led to the speculations, which is really what they are, that I presented to you, come from this book, where you'll find the evidence. Thank you very much. Thank you.